Hi, thanks for the chance to present on this. It's going to be a new type of talk for me. Actually, my research group at San Jose State, we've been the main thing we do is work on searching for rare gems. We've been doing for years, but in kind of an ad hoc basis and not really worked it through formally what we're doing. So this may be a little not entirely coherent talk. A lot of collaborators made this work possible. Just to highlight, there's several students here who have posters up, which you can get some more details about some of these projects. So I want to start off with just backing up and doing a little bit of a history lesson on sort of a success and failure story on searching for a certain type of rare gem or finding a certain type and see if there's some lessons we could learn from it. So this is a plot of, we call it the everything plot of stellar systems of a half-light radius or effective radius versus absolute magnitude, and putting galaxies and star clusters on the same plot. So this is like era 25 years ago, and at that time, you wouldn't even think about putting these objects on the same plot. You'd make a plot for galaxies, you'd make a plot for star clusters. If you're interested in those two different things, they're different communities, and you wouldn't mix them. They're just clearly two types of objects. There was even a name for this gap, if people thought about it, called the Gilmore gap. Um, there were some hints about some unusual things going on. These globular clusters down here, there were some oddball clusters, Mega Centauri, a couple of other objects that are unusually large, unusually luminous. We do know a lot more about these days, but there are clues to maybe something else going on that we were not seeing. And these clusters are all based on the Milky Way. Um, so fast forward a few years to this is a nearby Virgo dwarf, a Virgo galaxy in M60. And this object I've highlighted here, it looks like a star, but it's actually a tiny galaxy. And it was collaborator Jay Strader found this. It was the densest galaxy known at the time. Example was called an ultra compact dwarf with a half-light radius of 25 parsecs and a few times 10 to the 7 solar luminosities. Now, there's just to scale what that would look like compared to Omega Cyn, much larger, but still much more compact than a normal galaxy. So you can see it's pretty bright. It's an extreme example of what was fairly recent at the time called UCDs, or ultra compact dwarfs, discovered by Mikhail Hilker and Michael Drinkwater. And how did they discover these? Where they were not looking for them. They just kind of had spare fibers. They were studying the Fornax cluster, and they just put spare fibers on things, bright objects, and they found these new species of ultra compact dwarfs. I'm sorry, it was Virgo and Fornax clusters. And there's an example. If you go back 100 years, there's an old plate from Hubble where you can clearly see that he was already looking at ultra compact dwarf but had no idea. So these things were hiding in plain sight. And the question was, kind of cutting off the bottom, why were they missed? And this is what called the gorilla experiment. Uh, this is a radiograph of lungs, and oncologists will look at these kind of images to scrutinize them for little nodules or very tiny signs of cancer. I don't know if, and this was the study done where they gave this image to expert oncologists. I don't know if you already spotted it. There's this little gorilla they placed in the image, and something like 82% of the oncologists didn't see it, right? Because they were so busy, they're so specialized in what they were searching for that they overlooked something that was just staring them in the face once you knew what to look for. So, they could consider this a selection function or a window function. If there are extrasolar planet people here, you kind of maybe know the history of 51 Peg, how it was missed by a very famous person because of having a periodogram selection function that was not anticipating the extreme properties of that object. So that's one of the cautionary tales was when you select for things, and this ultra compact dwarf was actually also sitting in plain sight in the survey of globular clusters in Virgo, the famous ACS VCS survey. They had it, but they in their images, but it was not within their selection function. So interesting objects like that can be overlooked. And then the question is, well, the first question we had is, I was involved with this work with Jay Strader, and we thought, well, if there's no easy to find, there must be more of them. Let's go looking. So I had some undergrads quickly go looking, and pretty quickly found things just searching Sloan, using fairly straightforward SQL searches in Sloan, and they got on TV because of what they found. So I'll show you the first. Richard Bowe found what was the new densest galaxy around M59 in Virgo. down here. We got follow-up from HST. We got follow-up from AO spectroscopy to measure the kinematics and found a supermassive black hole in there, which is 13% of the mass of the galaxy, and it's a smoking gun for this being a strip nucleus. So this is now fast forwarding to the question of once you find these rare gems, what do you do with them and why are they interesting? And these turned out to be, UCD is very interesting for probing the collection of supermassive black holes that were unaccounted for. And a lot of them do turn out to have supermassive black holes. Michael Sandoval found another thing around another Virgo galaxy, which we call a hypercompact cluster. It's I think still the densest known free-floating stellar system. Half-life radius of 2 parsecs, but a 10 to the 7 solar mass. And this is kind of a unique object. We don't know about any. And this is another example of when you find the rare gems, what do you do with it? This is almost 10 years ago. We published this, and no one's followed it up. No one knows what to do with it. How do you explain this? Where does it come from? Is it telling us something interesting astrophysically? I don't know. We're kind of finding a lot of these rare gems, and it's a question of how do you convert that into science? Just another lesson for sort of people, working on archives and putting together these beautiful search resources. Well, we were lucky to find that first compact galaxy because it was 2013, and we were working with the Sloan DR7, and you can the object was there in the catalogs. But if we'd just gone 1 year later in the DR8, we would have missed it. There's these large sections of which they don't catalog around bright galaxies, and I guess the feeling is that that small fraction of the universe is not that interesting but if certain science goals, if you want to find objects around large galaxies, that's very crucial. So there's where it is. This is legacy, so it turns out it is in legacy, but for some reason it's classified as a point source, even though it's pretty clearly resolved. So I'm not sure what's going on there. But the bottom line is we still don't know how many of these things there are because no one's really done a proper search because you have to kind of go in there and do it manually if you need to at this point because the catalog tools are not quite there. So another rare gem. Has anyone thought about M32 as a rare gem? It's our nearby. I know Eric's written at least one paper on M32. So it's a pretty rare object, but the question is compact elliptical in the local group, well studied. Does anybody know of any other M32 exact analogs? I mean, I don't think I know any. There's some close ones, but I don't know how well they've been looked for. What do they tell us about galaxy evolution or anything? I mean, they tell us about accretion histories. Well, so our student group started going out and doing what we get the low-hanging fruit and try to at least find things with spectra that are compact ellipticals. They're not quite as compact as M32, so we've managed to find a collection of these, mostly accretion remnants. They're not all, there's at least one isolated one, so that tells us there's maybe these red nugget, fossil galaxies that are left behind. Yeah, and we got so busy at this that we formed our own band called Ultra. So we're still working on finding how more of these because they seem to be fairly rare. The latest is I've had a master's student working on a CNN network the problem is they look a lot like background galaxies if just have images and you don't have spectra. And so he's been working on a CNN to try to classify background versus foreground galaxies to find more compact ellipticals and UCDs. The tricky part is the training set is tiny, only 14 objects. So 2 tricks he used to actually, this is gonna be a success story, is that first do data augmentation, and the other trick is do transfer learning, is that do learning on the Galaxy Zoo classifications and then skim off the last layer and then transfer and do it for this new class of objects. And it turned out to work pretty well, at least in the validation steps. I'm going to be really convinced when we go out and we take spectra of a new candidate and see if we really hit a rare gem or not. Okay, so now moving on to some new classes of objects. I'm going to just throw out there some new classes of rare gems that we just don't know what to do with yet. One is something that we again found kind of accidentally. One of our master students at San Jose was involved in finding this this is part of the MADCACH survey where we found this, we initially thought was a UCD, it turned out to be a young faint fuzzy cluster. And we followed this up with HST to kind of confirm what it was. This fits in a part of parameter space that this is a young star clusters, and it's an unusually large star cluster, massive large star cluster There was this previous small cottage industry of what's called faint fuzzies or extended star clusters. Some of them in Virgo in the local group. Again, this class of objects that are different from globular clusters, are different from Palomar objects. No one quite knows what to do with it. There's some kind of hand-wavy ideas of forming in certain types of galactic collisions, but again, we don't know. We don't know how this thing formed. It looks like it was probably some product of a collision. Um, but there's this whole class of star clusters, and I'm not plotting the old ones on there, that again, they're fairly rare, and they must be telling us something about galaxy and star cluster formation, but we don't know what to do with them quite yet. And we've not looked systematically for more of these young ones. Another example of a rare gem, again, accidentally found, was working with Søren Larsen, is heading up a project of doing detailed abundance study of local group globular clusters. Really high signal to noise, and just kind of working through some of the brightest clusters in the local group. And we looked at this one around M31 called EXT. Oh, I didn't put the name on there. It's EXT8. And this is the high-res, part of the high-res spectrum of looking at one of the metal lines that turned out to be really weak, a metallicity almost down to -3, which was far below what was considered the metallicity floor for globular clusters of -2.5. Again, we weren't looking for it, just kind of happened to catch it with spectroscopy. And it turns out we call it the impossible cluster because in conventional globular cluster formation theory, you form it within a host galaxy, and there's a evolving mass metallicity relation. So to have a low metallicity cluster, you need a low mass dwarf galaxy at early times, but there's not enough mass in that gas in that galaxy to form a high mass cluster. This is a million solar mass cluster. So it sits in this part of mass metallicity parameter space. Sorry, that's cut off. We call the forbidden zone, so it shouldn't be there. And so this kind of defies our understanding of like, where did this thing come from? And we've started trying to look for more of these, but how much time? Oh gosh. Okay, but it takes a lot of spectroscopy. We're trying to figure out pre-imaging. So I will just skip to like, sorry, I've run out of some of these things. Maybe skip to one of the more interesting cases of ultra diffuse galaxies. Maybe talk about the one that the students are working on here. You might have heard about the no dark matter galaxies, a couple of dwarfs we found that appear to have no dark matter around a nearby galaxy group called AGC 1052, DF2, and DF4. Again, these were discovered accidentally because we were looking for things with lots of globular clusters. We thought we could have likely to have lots of dark matter in those galaxies and go out and measure the kinematics. It turned out to be the exact opposite. And it's just the dark matter that's weird about these things, is they've got very strange globular cluster systems where the clusters are unusually luminous, large, and monochromatic. It tells us that the galaxies sit in what's called a trail. And it looks like our best model for this is what's called a bullet dwarf collision, of high velocity collision of two galaxies, which I don't have time to go into, which could naturally produce all these different properties. So then the question again is, we kind of found these by accident. There must be more of them. How do we find them? And our hypothesis is that, well, if they're bullet dwarf collisions and these unusual globular clusters are natural part of that, let's go start looking for the globular clusters before we do the spectroscopic follow-up. And as was kind of mentioned in Legacy, I mean, these things are really bright and obvious in Legacy, but there's a shredding problem with the automated modeling. So you can't just go out and simply search for them. So I have a couple of students here. You can see their posters working on ways to deal with this. One of the ways we've been dealing with is just going through by eye. And so one of our students went and looked through 20,000 images. I thought that was a lot, but then I heard Mike Gladders looked at 900,000. So I guess we've got more catching up to do. Anyway, so he was able to find a couple of nice examples. This one we've been able to follow up with HST and Keck, and stay tuned. We're not sure yet if it has dark matter or not. So those papers will be coming out later this year. But that's another example of things that are sitting in the data in plain sight, but you kind of have to, all the search tools are not really optimized for finding them. So I'm just going to leave up, I'm kind of run out of time, leave up my sort of like general conclusions for what we learned from all these years of searching for rare gems. Thanks for your attention.